This is going to be a quick rundown of how we can connect a Cognex camera to a robot and how to actually calibrate it. So the reason I specify connecting it to a robot is we're going to be connecting it to the end effector, meaning the camera can actually move. As I said, the purpose is just to show the process of calibrating a camera that is mounted to a robot. The big clarification there is it means the camera is going to be taking pictures from multiple locations and that it's going to have almost a changing calibration. So that's the big difference. If you're doing a static method where either the robot is still holding the camera, but it always goes to the same place to take that picture, or the camera is completely statically mounted, then this isn't required, and just the regular Cognex manual will be able to walk you through pretty well on how that should work. Another thing to note is with just using this method, you're not going to be able to get depth and how far away something is, but you can add distance sensors or other sensors to kind of make up for that absence later on. All right, so the first thing that we're going to look at is, since this is specifically Cognex, we're going to connect to the Cognex cameras. I've got a Cognex camera sitting over in the other room that I can connect to wirelessly, so I'm going to use that kind of as an example. So whenever you pull up the Cognex Insight software, there should be a whole list of cameras on this left-hand side. If it does not find any cameras, that means you're not connected to them on the network, and it means that you actually won't get this view right here. So once we have it open, I'm going to go ahead and show you guys how to add cameras if they don't already exist. So if you are missing a camera in this bottom left section, that means that the robot can't talk to it or the computer can't talk to it. And that's most likely because it's not on the correct subnet. So to fix that, we're going to go to this add. And just for clarification, whenever I'm talking about a subnet, I'm going to hit show all because all of my cameras did show up. But if a camera does not show up in this left list, it should show up under new here. But back to the discussion of subnet. Whenever you're talking Ethernet IP communication, it is defined as these 4 values right here. On a local network, you will most of the time see 192.168, and then every group has their own preference on this third value. A lot of times it's either .0 or .1. With ABB robots, it's always .125. So as I said, every group has their own preference. And whenever I'm saying it needs to be on the same subnet, that means these first 3 values need to be the same as the robot subnet, which should also be the same as the computer's subnet. With that in mind, this 4th value has to be different. So Ethernet IP addresses are a lot like house addresses. No 2 families can really live in the same house, but they can live on the same block. So the subnet is kind of analogous to a block, while the IP address, this last value, is synonymous with the specific house / the specific address. So the default gateway, if your device needs to be able to kind of escape its local network and talk to outside networks, that means it's going to have to go through a gateway, which is exactly like what it sounds. It's kind of the gateway to get to other networks. Then you'll need to type in this, whatever IP address your gateway is set up on. 9 times out of 10, your camera is not needing to travel through a gateway, so it's kind of a moot point. If you're only on the local network, it won't matter at all. If you don't know what your computer's IP address is, you can hit this copy PC network settings, and it will actually copy the exact settings, and then you can go in and add whatever you want. Now, I'm not going to apply these changes because it will overwrite how I have the camera set up right now, but this is always an option. There is also DHCP connections. However, that's not going to be used a ton in industrial networks because you want everything to have a fixed IP address so the robot can always find it. If the IP address is constantly changing, the robot won't be able to find it. So we're going to go ahead and ignore that one. Now, one thing I want to point out while I'm looking in here is this little hand R camera. This is the camera that is located inside the Yumi's hand. It is technically a Cognex branded camera, but it does not tend to work great inside the Cognex software. So that's something to keep in mind. You want to use ABB software for talking to those kind of cameras. All right. We're going to go ahead and connect to just this left-handed camera real quick. I'm going to hit connect, and here we'll see it's connecting. So once we've connected, we're going to want to set up the image. Setting up the image is mainly just using this as a chance to get everything in focus. So this is where you'll be messing with the lens and making sure you have the settings on the lens correct. Starting down here in the bottom left, we're going to decide what triggers the camera. You've got a few different options. We don't use continuous very often. External works really well if you have a digital input to the camera that will be triggering it. Manual means it does have to be manually triggered from the software. And then network, industrial, Ethernet, and camera. All three are ones we use quite a bit. If you use camera, then it can either be communicated to with a robot or the software. And then a lot of times we will go ahead and use industrial Ethernet because we do talk to them via Ethernet IP. From there, just a brief overview of some camera words. I will not claim to be an expert on these, but we have exposure time. That is how long the sensor on the camera is actually accepting light. So as you increase that, let's go ahead and bump that up to 200 right here. That means it lets more light in, and you will see that the camera actually in the collab room in the reception room has moved, so it's getting a bad image. But if I bring this up to a ridiculously high amount, you'll see it's letting in so much light that even on black items, I'm able to see features. But this means that anything with even the tiniest amount of light coming from it will get whitewashed. And the higher exposure you're using, the more likely you are to kind of get a blurry image, because if it moves at all during this 1 second, it's absorbing light, then you'll run into a lot of issues. So we're going to bump this down to 50 again. And you can also do a live video while doing this so that you can get a more granular check of how it's affecting it. So I can go up to, 500, and I can see my changes a lot faster. Another interesting thing you'll note is you'll notice it's taking pictures a lot slower. That's because the exposure is so much higher. So if you have a lower exposure, that means that your pictures actually do happen quite a bit quicker. Auto exposure, exactly like what it sounds like. It will try to set the exposure for you automatically. And this start row and number of rows has to do with the pixel density on the robot or on the camera and where it's actually going to search for it. So don't worry about that too much. And then focus region is the last thing. So inside your picture, if there's a certain area you need to be in focus, you can move this focus region over it. And then as you twist the dials on the actual physical lens to adjust the focus, it will change the, go back to live video, it'll change this focus number to match how well you're actually in focus. The higher the value, the better off you are. You'll notice with it having such a dark image, it can't get an actual focus value on it. Another setting on the camera, more of the physical camera, is the aperture. So I've mentioned focus, which just affects the focal length. In other words, where you're going to get the cleanest image at a certain distance. The aperture of the camera is a small hole in the lens that can grow or shrink, and that affects how much light you let in. Now, the aperture does control the amount of light you let in, but it also has the benefit of controlling how in focus you are. The smaller that orifice is in that aperture, it means that you're going to have a bigger focal range that will look relatively clean. So the trick to that is you want to have your aperture as closed as possible, but still getting enough light in to get a good image. A few ways to do that is increase the exposure. That will let you get more light in, or you can have a nice backlight. Online is a great resource for how cameras work and the kind of importance of the focus, the aperture, and even more importantly, I don't mention it here, is controlling the light source of the camera. or what is shining on the object. If you control the light, you'll get a lot better images and be able to do a lot better machine vision applications. So now we're going to go into actually calibrating a camera. So on the bottom of the screen, I'm going to jump back over. We're going to go to setup image, and we have this calibrate option. Now we're pretty much always going to select grid for our calibration because that is going to give us the most accurate calibration. Whenever you look at this XY scale and edge to edge, XY edge to edge, what that means is you're going to select two edges that run about the length of the camera and use that to calibrate it. The problem with that is cameras tend to have a radial distortion, or the calibration in the middle is different than the calibration toward the edges. So if you try and use just a simple scale from left to right, you're not going to get a good calibration. With a grid, it's actually going to check the entire area that it can see a grid. So we're going to come over here and hit calibrate. This will bring up a nice little calibration window. With this window, we are going to go to setup. I'm actually going to hit cancel, and I meant to hit clear all so it doesn't. There we go. So we're going to go to setup, and then we're going to do a checkerboard with a fiducial. So the checkerboard is exactly like what it sounds. It's a checkerboard. The fiducial is this little L shape in the middle. And what that does is it gives a coordinate system to the camera. And the reason we want a coordinate system is it means that the robot is able to line up to it. Now, for grid spacing kind of determines the accuracy of your camera and is going to change based on how far away you are. So as the camera gets farther and farther away, it won't be able to recognize as small of squares, meaning that you may have to make this number bigger. But you want to make this number as small as you possibly can while having the camera still be able to see it. The reason behind that is the more squares it can pick up on, the more accurate your calibration is going to be, just because it has more data points to work off of. And then it does let you choose the different units, and you can actually print the grid straight from here. So it is nice that they auto create that grid. And if you do different sizes, so if I do a 5 mm or a 3 mm grid and hit print grid, you'll notice the squares are a lot smaller. Once again, that's how you get kind of that improved accuracy. So after we've done that, we're going to go to the pose image. And with this, you can trigger the camera again from here, and you'll see all of these little green dots that show up. These are all the corners and intersections of the checkerboard that it was able to spot. And that is what's going to decide the calibration. So I can go ahead and hit calibrate, and it will bring me over to the results screen where it will tell me how good my calibration was. You want to aim for as close to 0 as you possibly can. And sometimes you won't be able to nail it down that much. A few things you can do to help get a better calibration if you notice you're getting a poor calibration is either reduce the size of your squares, fix the focus on your camera, or you can do more than one pose. So you can set it up so that you can take multiple pictures. So whenever it says pose, it means that you can reposition this fiducial multiple times to cover the entire screen. So you'll notice this entire section over here is not being calibrated. Doing multiple poses means you can move the fiducial around to cover the rest of that area, because we don't always have the perfect size sheet of paper. So we're going to run back through that real quick. So we're going to get pose, wait for it to pick up all the features, hit calibrate, and hit OK. So this camera has been calibrated now. One thing that you need to notice on this is it's calibrated for one specific height. If you move the camera closer or farther away, that means the calibration is going to be completely off. 1 millimeter is no longer 1 millimeter, it's now 2. So the values do change based off that Z height. The most important thing is to keep that Z for the camera constant. So we're going to hop back over to the PowerPoint and talk about this a little more. Once again, these notes right here are things I all mentioned as we were walking through it. So Just make sure you use the smallest square as possible. The smaller the aperture, the better, but that may come at a cost of using a higher exposure or more external lighting sources, a few things like that. Typically, we aim for kind of the 0.5 range. Typically, if you're within 2, it's very functional for robot pick and places. It's not exceptionally important, but if you're trying to insert fasteners into a hole, then you're going to want to make sure that is as tight as possible. All right. Now we're going to get into the actual robot side of it. So one thing I want to make sure I mention one more time again is that if you make any adjustments to the aperture or focus of the camera after you've done that calibration in here with the calibrate tool, then you have actually changed and messed up that calibration. So you're going to want to do that again every time the focus is changed. Once again, only if you're actually picking and placing with the robot is that calibration necessary. If you're just trying to determine if something is present or absent, then that calibration isn't nearly as important. All right. So the first thing we're going to do whenever we are calibrating a camera to a robot end effector is you will need to place that fiducial down and then teach a work object at the origin of that fiducial. So if we look at this fiducial, where these solid fiducial lines come together and meet clear up here, if you were to project them forward, and if you also follow these little hint lines right there, where these meet is the origin, and we want to teach a work object that lines up with the fiducial. So you'll teach X1 here, X2 anywhere along these lines, and then Y2 clear up here. And the reason we're teaching a work object right there is because that will line up with the camera coordinate system. By taking a picture with the camera and putting its origin right here and creating a work object in the same location, you now have 2 frames that are lined up. Now, when teaching that work object, it is going to be really important to have a really nice TCP and also jog very slowly, because if that calibration sheet moves at all, you're going to have ruined your alignment between the camera and the robot, and you're going to want to jog slowly because it is very easy to stab through the paper. So wherever you put that fiducial down is where your camera origin will be placed. That means if you put your fiducial, such as in this case, clear up in the top left-hand corner of the image, this means that my origin for this image is located up here, and it's actually slightly angled. So just for simplicity's sake, a lot of times we do try and put the fiducial in the center of the camera. Just makes life a little bit cleaner and more sense. Or you can actually try and put your fiducial clear over at the edge and just visually line it up with the camera frame. That's nice to do whenever you want to make sure all your values are positive, for example. All right. So from there, you have most of the calibration set up. That is one of the slightly more difficult parts. From there, we're actually going to create a TCP on the robot that lines up with that same camera frame. So we did just create a work object, and that work object is where you will stop if you're doing a static camera mount. But if the camera is mounted to the robot and you want to take pictures in multiple locations, you're going to want a TCP or a coordinate frame that travels with the robot that lines up with the camera at all times. So the way we're going to do that is we're just going to inverse the transformation. So right now, whenever you have the robot in the position that the picture was recorded from, that will put the camera coordinate system back at the center of that fiducial and at the center of that work object. So we want to effectively create a TCP that is in the same location as that work object. I have taught a work object that lines up with the camera coordinate system. I now need to put a TCP at that same position, so at that work object. That way my TCP lines up with my camera coordinate system. Now, the way to do that is to set the robot tool to tool 0, and then make sure your work object is selected as that camera work object. And the next step will be to look at the values of the robot position. So it'll be an X, Y, Z, and rotation. Now, the way to think of that is that X, Y, Z, and rotation is a transformation. It is going from the work object you have selected to tool 0. We need the opposite direction. And whenever you need the opposite direction or opposite transformation, you can just take the inverse of it. And that inverse will actually be our new TCP. So tool 0 is the default tool on an ABB robot, and it is the flange of the robot. It is where all TCPs are based off of. So this is my 0 coordinate system for the flange of the robot. We will not jog the robot to teach this TCP because you're trying to teach a TCP that you cannot physically see, which makes it next to impossible to teach. So we're going to have to do it entirely mathematically, which is where if we have the transformation from the work object to the tool 0, we can then go the opposite direction, and that will be our TCP. So these next couple things show you how to calculate the inverse. For us, we will be using ABB a lot of times. If you have a different robot, there's Fanuc ones. And then if you want to use other packages, there is Polyworks. And you can also do the transformations inside Robot Studio. But in all honesties, just record the values from the robot in work object coordinate systems, hop online and find any inverse matrix calculator or any inverse transformation calculator, and it will be good enough. All right. From there, I'm just going to mention a bit on camera communication. I won't go in depth on this because every robot, everything you're hooking up to, whether it's a PLC or ABB or Fanuc, will all be a little bit different. But what you're going to need to look for is either the camera's manual or an EDS file for the camera. And EDS is just an electronic data sheet that kind of defines the communication for the camera. And this will tell you everything you need to know to communicate with it. A lot of times we will use Ethernet IP to communicate to the cameras. There is some exception with Cognex. ABB talks to them directly, so we don't always use Ethernet IP. But if this is your first time setting it up, Ethernet IP is a good go-to. The camera does operate as an adapter. So whenever you're talking about Ethernet IP, there is an adapter and server communication, also known as master and slave, where the robot acts as the server and the camera will act as the adapter. So the camera will only talk to one device while the robot can talk to many devices. That's what that's referring to. And then depending on the ability of the robot being used, Ethernet TCP can also be used, but that's often a lot harder to code. There are good examples for C# programs. So that is an option you can consider since Ethernet IP to a PC is not necessarily an option. Now, once you've done that, we can do a quick validation to make sure you have your TCP set up. With the robot still positioned in that same location it took the picture from, you can select the new tool and the camera work object. And since they're in the same location, they should be 0. So there should be 0 XYZ and there should be 0 on the rotation. If it's showing quaternions, then it'll be the identity quaternion. But that's a quick way of making sure that you actually talk the TCP correctly. All right. From there, kind of the operation that we'll use to run said system is, first off, anytime you take a picture, it needs to be at that same Z distance or the same distance away from the part that your original fiducial was taken from. Otherwise, your calibration is going to be messed up. So That is the one real limiting factor here. And other than that, all you have to do is position the camera over the feature that you're going to acquire an image of. Record the current robot position. So that's going to be a C-Rob T or an L pose in Fanuc. And after you've recorded that position, you're going to apply an offset. And that offset is going to be the XY values you got from the camera. What I mean by that is whenever you find a feature in Cognex, so we're going to tell the Cognex camera, we're going to create a quick, easy builder routine where we're looking for a pattern. And the pattern we are looking for is a checkerboard. Let's see how many of those it can find. It will only find one, is the idea. You can get Cognex camera to find multiples. I believe there's an option to find up to 50. So we'll see it found a little checkerboard right there. If we acquire a new image, we'll see some of these values. And this is where you will see a X value and a Y value. These are measured in millimeters because we did a calibration. If you have not done a calibration, it will show pixels. And then the last thing it shows is the rotation. And these values are what you will pass to the robot. So just as a quick example of that communication, scroll down a little bit. I do mention it in here how you can add an Ethernet IP device. Right now, the robot is not set up to accept one, so this communication won't work entirely, but I'll show you guys how to add it real quick. So we're going to go to communication and hit add device. Now you'll see there is an option for robot, and there's even an option for ABB. You can do the native robot. We are not going to be doing that because I'm going to show you guys how to do Ethernet IP specifically. So we're going to change it from robot to other. That way it doesn't lock us into one decision. And we will be using Ethernet IP. Most of our devices can communicate via Ethernet IP. That means it's kind of a good default one to go to. And hit OK. From here, we can start telling it what we want to send out. So we've got pattern 1. I'm going to tell it I want it to send out pattern 1's X value as soon as I don't pass it. So fixture X and fixture Y. And this is how you'll get the robot to send and receive that different data. Depending on how your robot communicates, it will affect your setup a lot on that. Once again, if you're specifically doing an ABB, you'll most likely be going through Robot Studio, and their software is very similar to Cognex Insight software, since it's actually built on the same underlying system. All right, but after you've taken that picture and gotten the XY value from the robot, you can then do it's going to be called a matrix multiplication or a pose multiplication to get the feature's location in the active work object coordinate system. The reason you want it in the active work object coordinate system and not just relative to the camera's coordinate system is because if you tell the robot to go to 1 millimeter and 2 millimeters, then it's going to try and go inside of its own base because that's 1 millimeter and 2 millimeters from the base of the robot. You need to make sure you take into account the robot's current position and then just kind of stack what the camera said on top of that. And the reason we're able to do that is because we lined the camera coordinate system and the robot's TCP up. So anytime you record the robot's position, you're also recording the calibrated location for that camera. And once you have the feature's location, you can go through and either insert a fastener, or if it's a more complicated motion, you can create a temporary work object located at that feature so that you can do a more complicated pick and place routine.